Hello everyone and welcome to Sally and Bytes. Today, I am here to teach Chapter 2, Data Representation and Boolean Logic, Part 3 for the Class 11 students of Computer Science. In this video, we are going to discuss about the Boolean logic, Boolean operators like and, or, not, logical gates and truth table. So let's dive in and get started. Have you ever wondered how computers can do a lot of things like human? How can a chip made up of silicon and wires do something that seems like it requires human thoughts? If you want to know the answer to this question, the first thing you need to understand is something called Boolean logic. Boolean logic was developed by George Boole in mid-1800s, who figured out a way to put formal logic into mathematical form. Consider an example: should I go to the park or not? Should I learn computer science or not? All these questions can have only one answer, either in the form of yes or no. Thus, a binary decision always results in either yes or no or true or false. Likewise, a switch has only two states: open and closed. An open switch represents binary 0 and a closed switch represents binary 1. The digit 1 or letter T is used to represent true value and the digit 0 or letter F represents a false value. A statement which evaluates either true or false is known as proposition or logical statement. 1 and 0 are two binary valued quantities that represent true or false state. Boolean logic is a type of algebraic logic that deals with binary values and logical operations. Boolean logic is widely used in digital electronics, computer programming, and other fields where logical decision-making is required. What is a Boolean variable? A Boolean variable is a variable that can take on one of two possible values, true or false. It is also known as binary variable, or a logical variable. One bit represents one Boolean variable. In computer programming and digital electronics, Boolean, binary, and logical variables are often used to represent logical values or states, such as whether a condition is true or false, whether a switch is open or closed, or whether a flag is set or unset. They are usually declared using a Boolean data type and can be assigned the value true or false. They are commonly used in conditional statements, loops, and other control structures to control program flow and make logical decisions. Next, what is a Boolean constant? The values which are stored in binary variables are known as Boolean constants. Therefore, the values true or false, yes or no or 1 or 0 are Boolean constants. In Python programming language, true represents the Boolean value of true and false represents the Boolean value of false. What is a Boolean statement? A statement is said to be a Boolean or logical statement if it has a definite value which is either false or true. Example of logical statement are: have you finished your homework? Is it raining? So the answer will be a definite value, yes or no or true or false. Next is the Boolean expression. A meaningful combination of Boolean operators and or not. Boolean operand or variable x, y, z, and Boolean constant 0 or 1 is known as Boolean expression or logical expression. Example 1. X plus y plus z. Example 2. A dot b plus b dot c complement. Example 3. U or v and not z. Here, we can discuss about the Boolean operators. Boolean operators are used in Boolean expressions to combine or modify Boolean values. There are three primary Boolean operators: and, or, and not. These operators can be used to create complex Boolean expressions that can be evaluated to either true or false. First operator is the and operator. And operator is a binary operator that operates on two variables, and the operation performed by an operator is known as logical multiplication. The symbol used for logical multiplication is dot operator. The AND operator returns true if both the operands are true, otherwise it returns false. Example x and y can be written as x to y. Now look at this table. Consider the following values for two variables x and y in this table. Now, when there is logical multiplication using an operator, the AND operation will result in true value 1, when both the inputs are 1, that is true or high, and for all other values it results in 0, that is false or low. Next operator is the OR operator. OR operator is a binary operator that operates on two variables, and the operation performed by OR operator is known as logical addition. The symbol used for logical addition is plus operator. The OR operator returns true if at least one of the operands is true, otherwise it returns false. Example, x or y can be represented as x plus y. Now look at the first table. Consider the following values for two variables x and y as shown in the first table. When there is logical addition using OR operator, the OR operation results in true value 1, when either of the inputs is 1, that is true, or both the inputs are 1, that is true or high, and for all other values of inputs it results in 0, that is false or low. Next operator is the NOT operator. The NOT operator is a unary operator that operates on one variable, and the operation performed by NOT operator is known as negation or complementation. The NOT operator is used to reverse the logical state of its operand. If a condition is true, then NOT operator will make it false. Example, NOT x can be represented by x complement. Now look at this table. Consider the table with values 0 and 1 for variable x. It means that the logical statements x and x complement are opposite to each other. If the values of a variable x is 0, its complement would be 1, and if the value of the variable x is 1, its complement would be 0, that is, x complement would be 0. A truth table is a table that lists all possible combinations of input values for a Boolean expression, and the resulting output for each combination. The number of rows in a truth table depends on the number of input variables in the Boolean expression. The output values in a truth table are typically represented using ones and zeros, where 1 represents true, known as tautology, and 0 represents false, known as fallacy. For example, a truth table for a Boolean expression with two input variables, x and y, will have 4 rows, since there are 2 power 2, or 4 possible combinations of input values. A truth table for a Boolean expression with 3 input variables, x, y, and z, will have 8 rows, since there are 2 power 3, or 8 possible combinations of input values. Now, look at this first table. Here's an example of a truth table for the Boolean expression x and y and x or y, which represents the logical and illogical OR of 2 input variables, x and y. There are 2 variables x and y, and the possible input values will be 2 power 2 is equal to 4 combinations. The possible combinations of input values of x and y starts from 0, 0 and ends in 1, 1. Now, look at the second table. If there are 3 variables x, y, and z, then the possible input values will be 2 power 3 is equal to 8 combinations. The possible combinations of input values of x and y starts from 0, 0, 0 and ends in 1, 1, 1. Here are some rules for writing a truth table. First, you have to identify the number of input variables. Determine how many different inputs your truth table will have. Each input variable can have only 2 possible values, which are usually represented as 0, false, or 1, true. Second rule. Determine the number of rows. The number of rows in your truth table will be determined by the number of input variables. If you have n input variables, there will be 2 power n rows, where n is the total number of variables. For example, if you have 1 input variable, there will be 2 rows. 1 for each possible value of the input variable, that is, 2 power 1 is equal to 2. If you have two input variables, there will be 4 rows, 2 to the power of 2, that is, 2 power 2 is equal to 4, and so on. Third rule is to fill in the input variable values. Write down all possible combinations of input variable values in each row of the truth table. Start by writing down all possible combinations of zeros and ones for the first input variable in the first column, then repeat the same pattern for the next input variable in the following columns. Fourth rule is to determine the output values. For each combination of input variable values, determine the corresponding output value based on the logical expression or rule that is being evaluated. This output value can also be represented as 0 or 1, depending on whether the expression or rule is false or true for that combination of input values. Fifth rule is to complete the truth table. Once you have filled in all of the input variable values and corresponding output values, your truth table is complete. You can use the truth table to evaluate different logical expressions or rules for the given input variables, and to determine the truth values of these expressions or rules for each possible combination of input values. Let's look at an example. Write a truth table for the Boolean expression f equals a dot b complement plus c by writing each step. Let's see the answer. We have to follow the given steps for writing the truth table. Step 1. In the given expression, there are 3 variables a, b, and c. Step 2. Draw 3 columns for each possible input variable combinations and 3 columns for each logical operations not, and, or n 2 power 3 is equal to 8 rows. You can see the first truth table created. Step 3. Fill in the input variable values. Write down all possible combinations of input variable values in each row of the truth table. Start by writing down all possible combinations of zeros and ones for the first input variable in the first column, then repeat the same pattern for the next input variable in the following columns. Now, look at the second truth table created. Step 4. Perform the logical operations b complement a dot b complement and a dot b complement plus c by considering the values zeros and ones written in each row for each input variable combinations and filling the rows for these columns with zeros and ones. For example, take the first row, which I have marked with red color. With values of a equals 0, b equals 0 and c equals 0. B complement equals 1. A dot B complement equals 0 and A dot B complement plus C equals 0. Now, try to work out by your own, by filling the other rows. You can check your answers by seeing the resultant truth table as shown here. Here, you have to note that number of columns equals number of variables plus number of logical expressions. That is, number of rows equals 2 power n, where n is the total number. Let's look at another example. Write a truth table for the given Boolean expression f equals a plus b dot c complement plus a complement dot c complement. Now, look at this table. Step 1. In the given expression, there are 3 variables a, b, and c. Step 2. Draw the columns for each possible input variable combinations. 2 power 3 is equal to 8 rows. Step 3. Fill in the input variable values. Write down all possible combinations of input variable values, starting from 0, 0, 0 and ends in 1, 1, 1 in each row of the truth table. Step 4. Perform the logical operations c complement a complement b dot c complement a complement dot c complement and a plus b dot c complement by considering the values zeros and ones written in each row for each input variable combinations and filling the rows for these columns with zeros and ones. Step 5. Now, perform the logical operations a plus b dot c plus a complement dot c complement. The resultant table will be a truth table, as shown here. Here, we can learn about the precedence of Boolean operators. Not operator, first precedence, and operator, second precedence, or operator, third precedence. There are some rules for evaluating Boolean expression. Evaluate the Boolean expression from left to right. Evaluate the expression in parentheses first. First, perform all not expressions. Next, perform all and expressions. And then, perform all or expressions. Precedence of operators can also be illustrated with the help of a truth table. Consider a Boolean expression x dot y complement plus z. In this truth table, not operations is performed first, that is y complement, followed by, and operation, that is x dot y complement, and finally, or operation is performed, that is x dot y complement plus z. Let's prove the following with the help of a truth table. X of y plus z equals x dot y plus x dot z. First, complete the truth table with the given expression of three variables x, y, and z, with 2 power 3 is equal to 8 combinations. Fill in the input variable values and perform the logical operations. Here in this table, both the values of x of y plus z is equal to x, y plus x dot z. I have highlighted it in blue color. Hence proved. Note that the order of precedence for logical operators is not, and, or. Let's learn about logic circuit. A logic circuit is an electronic circuit that performs a specific logical operation on one or more input signals to produce an output signal. It is made up of digital components, such as logic gates, flip-flops, and registers, that are designed to perform logical operations on binary inputs, that is zeros and ones. Gate is a circuit which takes one or more inputs and generates an output. Logic gates use the binary operators and, or, and not. The three main logic gates are and, or, and not. Now, let's learn about AND gate. In an AND gate, both inputs need to be 1 for the output to be 1. This is the picture of AND gate. If input A and input B are true, then output Q will be true. This can be seen in the truth table for the AND gate. The Boolean expression is written as Q equals A and B. Let's learn about OR gate. In an OR gate, at least one input must be 1 for the output to be 1. This can be seen in the truth table for the OR gate. This is the picture of OR gate. If input A or input B is true, then output Q will be true. This can be seen in the truth table for the OR gate. The Boolean expression is written as Q equals A or B. Next is the NOT gate. NOT gate is also known as a logical inverter as it inverts the input. The output is always the opposite of the input. This is the picture of the NOT gate. This can be seen in the truth table below. If input A is true, then output Q is not true. If input A is false, then output Q will not be false, that is true. The Boolean expression is Q equals not A. Let's learn about some more important logic gates. NOR gate. NOR gate is an OR gate combined with a NOT gate. This is the picture. NOR gate is a combination of OR gate followed by an inverter, NOT gate. It acts in the manner of logical operator, or followed by negation. Its output is true if both the inputs are false. Otherwise, the output is false. Next is the NAND gate. NAND gate is an AND gate combined with a NOT gate. This is the picture of the NAND gate. NAND gate operators as an AND gate followed by a NOT gate. It acts in the manner of logical operator and followed by negation. The output is false if both the inputs are true. Otherwise, the output is true. Next is XOR gate. XOR, or exclusive OR, a variation on the OR gate. If the two inputs to an OR are both high, then their output from the OR gate will be high too, but with an XOR gate the output would be low if both inputs are high. This is the picture of XOR gate. Here, you have to note, if NOT gate is added to the output of an AND OR gate, then the output of these new gates will be the opposite of the original AND OR gate. NAND and NOR gates are called universal gates because any digital circuits can be implemented using these gates. Let's see an example. Draw a circuit diagram corresponding to the following Boolean expression, f equals a dot b complement plus c complement dot d. Look at the picture. First step is to obtain the expression a dot b complement. Now, look at the input variables a and b on the left side. We draw a NOT gate from input b, so we get b complement. Now, we draw an AND gate for input a and b complement. As the result, we get a dot b complement. Second step is to obtain the expression c complement dot d. Now, look at the input variables c and d on the left side. We draw a NOT gate from input c, so we get c complement. Now, we draw an AND gate for input c complement and d. As the result, we get c complement dot d. Finally, we combine a dot b complement and c complement dot d with an OR operator to obtain the final expression f equals a dot b complement plus c complement dot d. Now let's see another example. Write equivalent Boolean expression for the following logic circuit. Look at the left side of the picture, where the inputs of the variables u and v are given. Input v has a NOT gate, so input v becomes v complement. Now, AND gate is given, so we obtain u dot v complement. Again, look at the left side of the picture, where the inputs of the variable u and w are given. Here, NOT gate is given for both inputs u and w. So, u and w becomes u complement and w complement. Now, AND gate is given, so we obtain the expression u complement dot w complement. Finally, we combine u dot v complement and u complement dot w complement with an OR operator to obtain the final expression, y equals u dot v complement plus u dot w complement. Now let's see another example. Write equivalent Boolean expression for the following logic circuit. Look at the left side of the picture, where the inputs of the variables u and v are given. Input u has a NOT gate, so input u becomes u complement. Now OR gate is given, so we obtain u complement plus v. Again, look at the left side of the picture, where the inputs of the variable v and w are given. Here, NOT gate is given for input v, so v becomes v complement. Now, OR gate is given, so we obtain the expression v complement plus w. Finally, we combine u complement plus v and v complement plus w complement with AND operator to obtain the final expression z equals u complement plus v dot v complement plus w. Let's discuss about the duality principle in Boolean algebra. This law explains that replacing the variables doesn't change the value of the Boolean function. The dual of the expressions can be achieved by, first point, replacing each and sign with an or sign. Second point, replacing each or sign with and sign. Third point, replacing each variable, such as replacing 1 and 0 and replacing 0 with 1. If the operators and variables of an equation or function produce no change in the output of the equation, though they are interchanged, it is called duals. Let's see an example. Find the dual of the following expressions, a dot b plus a c. The answer is a plus b dot a plus c. Second example. x dot y complement plus x complement dot z. The answer is x plus y complement dot x complement plus z. Thanks for watching. Watch the upcoming videos. Chapter 3. Computational Thinking and Getting Started with Python. Part 1. Which includes Introduction to Problem Solving, Steps for Problem Solving, Algorithm, Flowchart, Pseudocode, Computational Thinking and its Components. You can check the link in the description box below.